Alright, next type of graph here is an ellipse, a thing called an ellipse, and again it's a conic section, or a conic. Alright, how do we get that this time? Well, the circle comes when you cut it straight across like that. Now the ellipse comes when you cut on an angle. So when you cut on an angle, you end up with something that looks like that. So an ellipse, as we kind of all know, looks a bit like a footy oval. Now if I graph one like this, and we put our ellipse through here like so, there's our ellipse. Now, of course, mathematicians aren't necessarily happy with that. They have to try and find all sorts of relationships of things and all that sort of stuff. So there's these things that they look at called foci, directrix, and eccentricity. Alright, now these things are in specific places. Okay, so for example, you would have directrix out here, and you would have another one out here. So there are directrices, those green lines. Okay. We would have also the foci. The foci are points here and here. So they're our foci. Let's call that F and F dashed for our two foci. Now, this other thing, this eccentricity thing, comes about from, okay, the distance. So if we've got some point there, the distance from that point, and so that point, let's put that point there, that point P has coordinates X and Y. And the distance from that point to the focus over that distance from that point to the directrix, where it makes a right angle with the directrix, is known as the eccentricity. So eccentricity is focus to curve over curve to directrix. Okay, and it turns out that that is a constant. So it doesn't matter where that point P is on that curve, if you measure the distance from there to the curve and then from the curve to the directrix, and you figure that out, then that comes out as the eccentricity. So for any particular ellipse, that eccentricity is between 0 and 1. Okay, so it could be anything in between 0 and 1, but for a particular ellipse, it's the same value. So if an ellipse has one of an eccentricity of a third, then it's the same for every point on that particular ellipse. Okay. Alright, so these are funky things that mathematicians kind of like to dream up and do. So let's just clear this screen and look at what some of those things are. Okay, so there's what we had. Now, let's have a look at some of these relationships that occur. So at this point there, we know is point P, and if this point here is point D, so we know that eccentricity is equal to Fp over Pd, and for an ellipse it's between 0 and 1. Okay, foci, there's two of them. One of them is F, which is AE0, and the other one, F dashed, is at negative AE0. That's for this particular one. So this is the one we've got the centre at 0, 0. Okay. Our directrices, as they're called, two of them. We have two of them. X equals A over E, and X equals negative A over E. And what are A and E? Okay, well, A is what's called the semi-minor axis, and so that's the distance from the centre to the outside. So A is semi-minor axis, and B is the distance from the centre to out here on the y-axis, and B is called the I've mucked that up, got them the wrong way around. Sorry about that. So A is a semi-major because it's bigger, and B is a semi-minor because it's smaller axis. Alright, now there is a relationship between those. Alright, these are not just random things, so these things don't end up being random. There is a connection. Alright, and remember in maths there's lots of patterns in things, and there is a relationship between B, A, and the eccentricity, and that's the equation that relates the three things together. Alright, so these directrices, focal points, semi-major, semi-minor axes, they're not all just random, they are connected. That's the kind of thing that mathematicians like to do. They like to find connections, they like to find patterns. Alright, what does it mean though? Well, if you look in your textbook and you want a proof of this, and you can see that on pages 343 and 45, but basically you end up with something that we may already or may not be familiar with, and that's the general form of our ellipse. So x squared on a squared plus y squared on b squared equals 1 is that, and your A and your B are semi-major or semi-minor axes. Alright, so that's alright if we've got centre 0, 0. What if we have a translation? So if we have a translation, so we end up with the centre now at H and K. So basically all that means that everything gets translated. So if it's got the centre H and K, then we've got foci. And the foci are plus or minus AE plus H, there's the translation, and K, there's our translation. Our directrices, end up at x equals plus or minus A over E plus H, so there's our translation. Of course, the eccentricity is between 0 and 1, and the translation goes into our Cartesian form, x minus h squared plus y minus k squared over b squared, and that equals 1. And of course, the semi-major and semi-minor axes are connected by the eccentricity in that way. Alright, so here are all things for ellipses. Okay, so we need to do an example. So, sketch x plus 1 squared over 25 plus what? Y minus 2 squared over 16 equals 1. Alright. Okay, so and then we're going to give the foci and directrices. Alright, so a few things that we need to do here. Okay, A, square root 25, so 5 for that. B, square root 16, 4 for that. Then if we're going to need to get the foci and the directrices, we need the eccentricity. And the eccentricity is connected by b squared equals a squared 1 minus e squared. So if we put that in, b squared is 16, a squared is 25, 1 minus e squared. Okay, divide by 25. Rearrange, etc., we get that the eccentricity here will be 3/5. Alright, so then we've got a whole bunch of stuff that we can do from that. What do we need to know? Centre. Centre's from our h and k, so it's minus 1, 2 for that. Foci. Foci are plus or minus AE plus K plus HK, I should say. So when we do that, that's plus or minus A times E is 3. 3 plus negative 1 and K, which is 2. Alright, so we would have two of them. One of them positive 3 plus negative 1, so that's 2, 2. Negative 3, take another one, negative 4, 2. There's our foci. Directrices. Okay, using them, x equals plus or minus a over e plus h. And when you put that in. You get plus or minus A, which is 5, divided by 3/5, plus -1. And when you figure those out, you get x equals -28 on 3, and x equals 22 on 3. Okay, so that would be all our information. So now we need to just go ahead here and sketch it all. So let's clear all of that. Here's our Cartesian. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so centre. Our centre was at -1, 2. So -1, 2, there's our centre. Okay, our foci was at 2, 2. So foci two, 2, and the other one is at -4 and 2. There's our other foci. I might need to extend this down here a bit more, I think. Alright, so there's our two foci. Our directrices, one of them is at 22/3, which would be 7 1/3. 1, 2, 3, 4, 5, 6, 7 1/3. There's that one. And the other one's at -28 on 3. And so that's -9, 5, 6, 7, 8, 9 1/3. About there somewhere. Alright, and so there we go. There's that. Alright, our semi-major and semi-minor axis. The semi-major axis is 5 in the x direction, so from our centre we go across 1, 2, 3, 4, 5, we end here. And the other way, 1, 2, 3, 4. Up that focus got it in the wrong spot because -4 is there. Hope you picked up on that. Okay, so again, 1, 2, 3, 4, 5. So that puts us there. And our semi-minor axis is 4, so 1, 2, 3, 4, and 1, 2, 3, 4. Alright, and there she is. There's our ellipse, and of course if you have decent graph paper, unlike what I've got there, then you should get the right answer. Okay, so that's it for ellipses. So this new stuff is new, this directrices and all that stuff is new to you. So yeah, it's a matter of, like a lot of new stuff, just getting used to it. But, you know, remember mathematicians like doing this sort of stuff. And there's a relationship between all of that stuff, you know, the focus and the centre and the directrices and the semi-major and minor axes, they're not random things, they are all connected by those formulas. Alright, so that's problem set number 2.